So this is one part, and then let us try to take up the next part, the spanning tree. Some issues like spanning tree, rank, and nullity. Okay. So the graph NE, let's say I will take a 6-9 graph like this, some 6-9 graph. Okay. Okay, of course, graph will not always be a diagram. You should know that it is a matrix. Okay, it's a matrix, and it is either incidence representation or adjacency representation. Okay, so okay, if the graph is composed of many disconnected graphs, of let us say k disconnected graphs, each disconnected component is a connected component. Therefore, for each component, there is a tree. Therefore, the total tree structure for this graph is not one connected component, but several trees. Then it is called a forest. If the graph is basically a disconnected graph, then what results is not a tree, because each component gives rise to a tree, and the set of trees will make a forest. So the tree structure that you generate for a disconnected graph is called a forest, because each component will give rise to a tree. Okay, so that's called a forest. Okay, that's called a forest. Now anyhow, we shall consider one single connected graph, 6-9, and I have to convert it into a tree, which is naturally 6, and 6 minus 1, 5. So 9 should be converted to 5. All right, so consider this tree. This is a tree. Okay, x1, x5, x4, x8, x9. You have applied any one of several algorithms which you have just learned today, and you will get one tree like this. Now let us go further. This is a tree that I have chosen. All right, please note these branches, I mean these edges which are red in color, indicate the edges present in the tree corresponding to this graph. The edges which are present in a tree are called branches of a tree. These are all branches. They are defined as branches. Okay, and with reference to this tree, of course, this is not the only tree. There could have been many other trees. There could have been other tree configuration also possible. There are many trees, but this is one of the tree. With respect to this tree, x1 is a branch, x4 is a branch, x5 is a branch, x8 is a branch, x9 is a branch. x2 is not present in this tree. What is not present in the tree, or what is not a branch, is called a cog. X2 is a cog. Okay, x6 is a cog. All right, x7 is a cog. All right, okay. So the edges constituting a spanning tree are called branches. So they are called branches. So x1, x4, x5, x8, x9 is a branch set. So the edges which are not in the spanning tree are called chords, or the chord set. The chord set is T complement. So they are the edges which are not present here, x2, x3, x6, x7. All right. Okay. So the number of edges present in a tree is called rank. Rank is equal to n minus 1. The number of edges present in the chord set the number of edges present in the chord set are the edges which are absent in the tree. They constitute nullity. So null, absence. It is presence. Presence is rank, absence is nullity. So rank is n minus 1. What is nullity? Total number of edges minus the edges present in the branch set. So total number E minus rank, E minus n minus 1, E minus n plus 1. If it is a k component graph, rank is n minus k, and if it is a k component graph, nullity is E minus n plus k in a k component graph. Okay, so rank and nullity, these two are very important, and this nullity is called a cyclomatic number. I shall just tell you why it is a cyclomatic number. Anyhow, before telling you, I shall give you the hint. You have the tree diagram here. All right, and by definition, apply that definition. Try to remove any edge. that will definitely disconnect this tree, isn't it? That is why a tree is minimally connected. Now, what was another definition? All vertices are connected, and there is one and only one path between every pair of vertices. Take any pair of vertices, there shall be only one path. And what is the third definition? There are no circuits at all. What is the fourth? A connected with n minus 1 edges is a tree. Now you can verify all of them. But now my point is, x2 is a card, isn't it? Forcibly try to bring a card here, x2. What is it going to do? It is going to create a circuit. Is that okay? A card is going to create a circuit. So one circuit gets formed when you insert one card. So one cycle is formed when you insert one card. Therefore, the nullity is called cyclomatic number. That nullity, it shows that mu number of cycles can be created by inserting one card at a time. One card at a time. That is why it is called cyclomatic number. Is that all right? So total number of edges is rank plus nullity. Total number of edges is naturally rank plus nullity. Nullity is represented by mu. Okay. Whatever. And the tree is T, the branch set union the card set. Branch set union card set is the total tree. Okay. All right. So now whatever I just showed on the diagram, I have put it here. One card inserted into the spanning tree gives one circuit. Just now I explained that. That is called a fundamental circuit with reference to that spanning tree. And you note that there can be many spanning trees possible. The fundamental circuit is defined with reference to a specific spanning tree which is in mind. So given one spanning tree, and that spanning tree partitions the edges into a branch set and a card set, and you choose only one card from a card set and insert it into that spanning tree, then it results in one circuit, and that circuit is called fundamental circuit. Is that okay? So now you can see there is one fundamental circuit made up of x1, x4, x2. X1 and x4 are branches. X1 and x4 are branches. X2 is a card, and if you bring x2, it will create one fundamental circuit, which just now I explained in the previous slide. Similarly, I can consider tau x3, circuit x3, x1, x5, x3, x1, x5, x3, tau x6, x5, x6, x4, like that. Okay, and tau x7, x4, x5, x7, x8. All right. So the number of fundamental circuits is definitely finite, which should be equal to nullity in number. As many cards are there, so many fundamental circuits shall be there. These are fundamental circuits. Don't get confused with all possible circuits. There are differently many possible circuits in a graph, but all possible circuits do not make a fundamental circuit. They don't make the fundamental circuits. Fundamental circuits are defined with reference to only a given spanning tree. And this fundamental circuit always will be finite in number. No doubt the total number of circuits is also finite in number, but these are more important because these are all derived with reference to a particular spanning tree. The set of fundamental circuits constitutes a cycle space. It is a space of all fundamental cycles. Is that okay? It is a cycle space. Okay. All right. The total number of circuits in the graph is finite. Okay. Any circuit can be expressed in terms of fundamental circuits. So you give any circuit, they can always be derived from the fundamental circuits, and the fundamental circuits are derived from a spanning tree. Note that. So a spanning tree is the central lifeline. It's a sort of lifeline of the entire graph. So the lifeline spanning tree defines all fundamental circuits, and from the fundamental circuit you can derive all other circuits present in the graph. All right. Okay. Any circuit will be a fundamental circuit of one or the other spanning tree. This is beautiful. So you take up any circuit, and if you want to make it that a fundamental circuit, you can always choose one spanning tree such that that becomes a fundamental circuit. This is a very beautiful concept. Okay. All right. Other spanning trees, let us see how to obtain other spanning trees starting from one spanning. I'll start with one spanning tree and I want to get another spanning tree. Quite simple. Just now I have told you, into a spanning tree, bring back one card that will make a circuit. And I told you the definition of a tree is circuitless. So the circuit which is formed, break the circuit, then it becomes a new spanning tree. Let us see what is the algorithm. Graph NE, convert it into a tree. A tree is n and n minus 1, n vertices and n minus 1 edges. A tree constitutes a tree set, a branch set, and a card set. Now, using the card set, introduce only one card. Insert only one card into T1. That creates only one fundamental circuit. Now break that circuit. How to break? Tree should be circuitless. How to break? So break the circuit by removing an edge in that circuit. How to remove? Not that card which you brought in should be removed again. You should remain such that retain the card introduced and make it a branch in the fundamental circuit. Okay, so retain that card, make that a branch, and the one of the old branch, remove that and make that a card. Is it okay? Make that a card. Which, suppose there are two branches already and a card. Now this card becomes a branch, no doubt. Out of the two, you can remove any one of them. There is a choice for it. So many spanning trees can be generated. All right, so you can generate. So this is called cyclic transformation to obtain all spanning trees of a graph. All right, now our job is to obtain the minimum spanning tree. Okay, so a new spanning tree results. Okay, so this is cyclic interchange or elementary tree transformation algorithm. So doing that, I have drawn some three such three such spanning trees, which means you can really generate many spanning trees starting from a graph. All right, many spanning trees. Now, once this is a tree, this one is a tree. Let us look at an interesting application. Let us assume that this is the representation of a big text, a big paragraph, very big write-up. Okay, very big essay. Therefore, a tree can be considered as a summary of an essay. This is the summary written by candidate number 1. This is the summary written by candidate number 2. This is the summary written by candidate number 3. So all are summaries only because they all satisfy all the characteristics of a summary. That it should have only n-1 edges, and it should not have any circuits. Yes, perfectly right. So there are different summaries possible. However, surely you can always tell this is a good summary, this is a little better summary, or there is a difference between this summary and this summary. There are a lot of similarities between this spanning tree and this spanning tree. So now both of them are derived from the same graph. Therefore, there must be some similarities. There must be some dissimilarities also. In such question, what is the distance between this spanning tree from this spanning tree? What are the similarities? Let us say similarities: x2 is present, x2 is present. So that is a similarity. x6 is present here, x6 is present here. That is also a similarity. x9 is present here, x9 is present here. That's also a similarity. x8 is present here, x8 is not present here. So that is a dissimilarity. x4 is present here, x4 is not present here. That is a dissimilarity. Or here x6 is present, here also x6 is present, similarity. x7 is present, but x7 is not present, dissimilarity. x1 is present here, x1 is not present here, dissimilarity. So you can express similarity and dissimilarity between these two. Okay. So what is the distance? Distance is defined as the edges which are present here but not here. The edges which are present here but not here. So x7 is present here, not here. x1 is present here, not here. Therefore, the distance is 2. Similarly, let us see here. x4 is present here but not here. x8 is present here but not here. Therefore, the distance between t1 and t2 is 2. the distance between T1 and T2 is 2. Therefore, you can find out the distance between T1 and T3. You can find the distance between T2 and T3, between T3 and T2, between T3 and T1. Like that, you can calculate the distances. Okay. So, what is the definition of a distance? So, the distance is the edges in T1, but not in T2, or edges in T2, but not in T1. So, mathematically, the distance is make the ring sum union of T1 and T2, ring sum union of T1 and T2, and find out the total number of edges present in the ring sum union of T1 and T2, half of it, half of the total number of edges present in the ring sum union of T1 and T2 is the distance. Okay. Now, a simple interesting question would be whether this distance is a metric or not a metric. All right. Another interesting question is, given a graph, you can generate many number of trees. Out of all those trees, which is the most central tree, or which is the tree which maintains the minimum distance from all other trees, or which are the two trees which are most maximally distanced, which are the two trees for which the distance between them is highest. So these are all the interesting questions. Okay, one question, start thinking, what can be the maximum distance between any two trees? Start thinking, what can be the maximum distance between any two spanning trees? Okay, okay, I shall give you, you find out. The maximum distance between the two spanning trees could be minimum of rank or nullity. Why? See, rank is the total number of edges present in a tree. So you can think of a new tree where all R edges can be replaced, provided card set has more than R number of edges. Only then you can do it. If the card set is less than R, at most you can replace only mu number of edges. Therefore, the maximum distance between two spanning trees shall be the minimum of rank and nullity. Minimum of rank and nullity. All right. So you can prove it little leisurely, and there is no board, and therefore you may not be able to get it, but prove it, and try to get it. Of course, you can always refer some books also. So a graph, when it has got a set of spanning trees, which one of them can be considered as a central tree? As I just now told you, the one which tries to maintain smaller distance with all other trees, with all possible trees. Quite a big algorithm, but anyhow, it's quite a big search algorithm. Anyhow, writing a code is not a big issue for this. Okay, all right. So spanning trees in a weighted graph. You know that just now I have told you the spanning trees in a weighted graph could be two algorithms, Kruskal's algorithm and Prim's algorithm, and surely I will not cover it. Please pick it up from your earlier notes of algorithms class. You have already done it, Kruskal's algorithm, Prim's algorithm. But my interest is not Kruskal's algorithm or Prim's algorithm. My interest is to construct a spanning tree, no doubt, to construct a spanning tree, but degree of the spanning tree is constrained. Like I will just give you the example over here. You saw that several spanning trees are constructed. I might put a condition. Look, the maximum degree of any vertex here is 1, 2, 3, 4. I might put a condition. The maximum degree of any vertex in the spanning tree should not exceed 3. Then this is not a valid tree at all. If I put that condition, then this cannot be a valid tree. Of course, this becomes a valid tree because maximum degree of any vertex does not exceed 3 here. In fact, it is 2. Because it is 2, it is a Hamiltonian spanning tree also. Now, this is also acceptable because it is 3, and I have told not to exceed 3. Not to exceed 3. Therefore, this is acceptable, but this is not acceptable. Do you get it? So I would be more interested in constructing such type of trees like degree constrained spanning tree. They are the algorithms. So now I would tell you have got to use Kruskal's algorithm to get the minimum spanning tree, but In addition, you have got to satisfy a constraint on the degree that it should not exceed 2, or particular, I might even mention the particular vertex. The fifth vertex should be exactly 2-degreed vertex, or I might even tell the fifth vertex must be a pendant vertex. These are all the constraints that I shall impose. Under the constraints, what is the minimum possible weight? What is the MST under constraints? Okay, that is the issue, and that is how you have got to modify in this in these assignments. If there is a question on the assignment, or what you have got to think is how to construct a minimum spanning tree under degree constraints. Okay, what you constructed in your earlier class, in the algorithms classes, where no such constraints were imposed. It was simply the application of Pascal's algorithm or Prim's algorithm, but here degree constraint spanning tree. Okay, hope I have made it very, very clear. The other point, other interesting point, I'll just tell you. You can construct, there are randomly given, lot of points would have been given. Okay, let me see if it is available. Some diagram is Pascal's tree, Prim's algorithm. I told I will not do it. Okay, I will not do it. I will not do it. I will not do it. This is Prim's algorithm. Okay. Oh, I don't have. Okay. All right. Okay. So if there are a lot of samples, let us say m number of samples of 2-dimensional space. Let us assume 2-dimensional space. Make it simple, or any 3-dimensional space. Then you construct a distance matrix from from sample 1 to sample 1, from sample 1 to sample 2, sample 1 to sample 3, sample 1 to sample m, like the 2 to 1, 2 to 2, etc. Okay, naturally this is a distance matrix, which is naturally an adjacency matrix. So now, because you are considering all possible distances, it is a complete graph. Is it all right? It's a complete graph. So this adjacency matrix is a complete graph. Then using this complete graph, construct, using Prim's algorithm or Pascal's algorithm, construct a spanning tree. All right, construct a minimum spanning tree. Minimum spanning tree. So there will be a minimum spanning tree. Minimum spanning tree still connects all vertices. All vertices. In other words, all samples in the population are still connected because of minimum spanning tree. Then try to define undesired edges, undesired branches in the minimum spanning tree. Like some branches are of higher weight. So you try to define them and remove them. When you remove them, what you get is disconnected minimum spanning tree. Each disconnected component tries to act as a small spanning tree. So that is a cluster. That is a class by itself. So Zan's algorithm produces the internal classes by constructing first a adjacency matrix, then constructing a spanning tree, and then removing the edges in a undesired edges. You have to define the undesired branches, remove them, and then you will get the classes, the clusters. So remove these undesired branches. A MST breaks into a forest of connected components. Each connected component becomes a cluster. Okay, all right. So this is Zan's algorithm, which will be very interesting. I think I had almost given this question in this cycle, but I had not through constructing a spanning tree. Okay, all right. So these are the types of advanced problems that you have got to solve here. Okay. All right. Now, starting from A matrix or X matrix, you should get T and T complement matrices with respect to spanning tree. These are all the assignments. Okay. Now, naturally, I want you to think of compressed representation of all these matrices. Okay. So you have known the incidence matrix. You have constructed the matrices of all fundamental cycles. So fundamental cycles. So if you have a transpose of that matrix and multiply, it becomes 0. Why? And can this be used as a condensed representation, compressed representation for representing a graph? That's what you have got to explore. Good. These are the things that you would be doing, and I have already given the set of assignment on this tree coverage to you. All right. Of course, it will be issued to you only by next week because you complete assignment number 4. What is